Okay, so this P3 video is about reducing energy consumption and reducing environmental impact as well, which is basically what the whole of the last section of P3.3 is about. If you read the specification, it's got quite a lot of confusing language, but I'm going to try and break down what they're talking about for you in sort of slightly simpler terms. Okay, so the basic upshot of this is that we're trying to avoid wasting energy at any point, because if we waste energy, it's basically more expensive, and it's worse for the environment because any negative consequences of any power stations we have to build are just bigger, okay, because we need to build more of them. So, three main ways that energy is wasted if we're talking about electrical energy being generated in power stations. First of all, during the generation, so when you use the power station to transform one type of energy into electrical energy. And to understand that, you need to know about all the different types of power station. We're not going to talk about those in this video, so that would be a separate thing for you to learn. But if you do understand that, it will help a lot with this stuff. Second thing is during transmission to where it's needed. So again, to understand this in enough detail, you need to know about the national grid and how that works. Not a subject for this video, but if you do know it, then you'll be able to do this kind of thing. And finally, during the transformation in the appliance being used. So some appliances are more efficient than others at transferring the electrical energy they get from the mains into whatever energy type they're trying to produce. So for example, sound for a radio. Okay, so here's an example of that, you know, if we're using a thermal power station, like a coal power station which uses hot steam, then some of the energy escapes in the form of thermal energy escaping from the steam and the cooling towers in the national grid. Even though there are steps taken to reduce it, which is to use high voltage, the transmission cables will heat up and they will therefore lose thermal energy to the surroundings, and a computer, say, connected to the mains will heat up during use and it will lose thermal energy that way as well. So that's just an example of those three things. Now, when we're talking about energy transfers, the most useful thing for us to think about is a Sankey diagram. So, here's a Sankey diagram that sort of represents what we've just been talking about. I'm going to run you through this, okay? So, we put in an energy source, so from a fuel, for example, if it's a coal-fired power station, or this could be from wind or water if it's hydroelectric, okay? And remember that the convention we have here is that the straight arrow forwards is the one we're trying to get to. So what the whole point of this is to try and get useful energy out of our appliance in the home. Okay. Now this would also apply to any factory and industry or anything else that's connected to the national grid. So we're going to talk about it in terms of appliances, but the same ideas will fit to any other electrical energy use. And then we have an arrow branching off to the side for each point of wasted energy that we talked about already. So we've got energy wasted in the appliance, is this last arrow here. We've got wasted energy in transmission in the national grid, and we've got wasted energy in the power station. So this is a reasonably complex Sankey diagram, but it's no different than any simpler ones that you might have seen. Okay, we've just got three waste energy arrows at three different stages, and the useful energy coming out at the end. So we're going to talk about our discussion in terms of this Sankey diagram. So I'm going to pop it up in the left-hand corner here to remind us what we're looking about, and then think about what we're trying to do is reduce the amount of fuel burned at a power station, for example. Okay, and the reasons that's good is because it will reduce environmental impact, it will mean fewer power stations. So in order to do that, the basic idea is we need a certain amount of useful energy. We can change that by sort of doing things sensibly, like, you know, switching off appliances when they're not being used, not using them on standby. So that's something we can do, but the main thing we can do is to reduce waste at each point. Okay, so for example, if we improve the efficiency of appliances, you can see what we've done here then is we've shrunk the width of the wasted energy arrow in the appliances. That's what improving the efficiency of the appliances or an industrial process does. Same thing here. If we were able to do it, improve the efficiency of the national grid, so waste less energy in transmission in the national grid, that would shrink the width of that arrow. And finally, of course, improve the efficiency of power stations. So all of these efficiency improvements the upshot of them would be to reduce the amount of energy we need from our fuel. Okay, if we go back just for the second, look at the width of the energy arrow in here. Right, it's quite wide, and then we go forward again, and we've reduced the width of the energy arrow that we're putting in here. That means less fuel burned. Okay, so making any of these three improvements will reduce the amount of energy needed from fuel or the number or size of power stations needed. So if we were building wind turbines, for example, we might only need to build 40 wind turbines rather than 60 wind turbines for a given use if we'd done these savings. Okay, so they're good things to try and do. Of course, they cost money to develop these efficiency savings, but as the price of fuel rises, that might turn out to be a very, very sensible thing to do purely from like the economic standpoint, purely from how much it's going to cost us. It might actually end up being worthwhile. Never mind any environmental impact that it might have that's going to be better than what we currently do. Okay. So, just to summarise then, the advantages of increasing efficiency are fewer power stations or smaller power stations. And this is where your knowledge of the types, disadvantages of each type of power station come in, right? Every power station has some disadvantages, and if they're anything to do with environmental impact or at all, then basically, if you're building fewer power stations or smaller ones, it will reduce that environmental impact. So, less carbon dioxide release from fossil fuels, less radioactive waste from nuclear power stations if we increase the efficiency of them. Okay? And the other benefit is it will reduce the overall cost of electricity, because if there's less waste, then there's less need to generate, and that means the cost will go down. Okay? So, the slightly different effect depending on where we increase the efficiency. If you have a more efficient appliance in your home, that means that you have less electrical power coming into your home, and therefore you get charged less money. So increasing the efficiency of appliances will save money for the consumer. That's why there's a big sort of emphasis now on like advertising in some aspects how efficient the appliances are, and you can see the energy efficiency stickers on appliances when you buy them. If you increase the efficiency of the national grid or the power stations, that basically saves money for the electricity companies, because to provide the same amount of electrical power to your home, they need less fuel, less power stations. Now, sometimes they might pass that cost saving on to the consumer, so they might lower electricity prices. Other times they might keep the money to invest in developing more efficient technologies and things like that. Okay, so let's put this stuff into practice then and see how we can use these ideas that we've looked at in a 6-mark question, because very often these kind of ideas take place in the context of a 6-mark question. They're really well suited to it, so you'll see a lot of them. And very often you'll get something like this. You'll get a table of data which you're asked to look at and choose an option from the table by weighing up the advantages and disadvantages. Now I'm going to show you one for choosing a particular appliance for the home, but you've got to bear in mind this would also work for a power station. If you had a table of data that compared two different types of power station, for example, you can use the same kind of ideas. Okay, whenever you get data in a table in a 6-mark question, it's a really good idea to quote the data in the table at the very least. So you pull some of these numbers out and discuss them. Compare the data mathematically. So in other words, what's the difference between them? How many times more is one number than the other? Those things often get you marks. The highest marks are often reserved for actually doing calculations from these quantities, so to work out another piece of information that's not included in the table that might be more useful for you. And then the final thing, don't forget to do this, is actually come to a conclusion about which one you would pick and why. Now, very often there will be a sort of equal number or roughly equal number of advantages and disadvantages to each type of appliance, and your conclusion isn't really, you don't really get any marks for which thing you choose. You get all the marks for the justification. You can see this command word here, justify. That basically means discuss and compare and come to a conclusion. That's what the code justify means. Okay? So, you can have a go at this now, and then try and use all the data, and then I'll show you a model answer for it. Okay, so here's a go over the model answer. I put the table in the top left so we've got it to refer to. So the first thing we're going to do is to look, there's several ways to do this. I'm going to look at sort of the main advantages of one TV over the other. So to start with, TV B, some clear advantages over TV A. It costs £200 less. That's an advantage to the consumer. So again, we've done 500 minus 300 to get the 200. You get credit for doing that simple calculation, okay? And it should last 50% longer. So I've presented this data in a slightly different way. I've worked out what percentage increase there is between 6 years and 4 years, right? So it's 50% more, an extra 2 years. If you're not happy about percentage increase and decrease, there's another video that I've done that I'll put the link in here for, and you can go and look at that. And as a result of the fact that TVB is smaller and cost less, there should probably be fewer materials and lower energy cost to using TVB. So in other words, it should have cost less for it to manufacture. All right. Now, the advantages of TVA, well, it's got a larger screen. You mustn't forget these things, right? That there's often some sort of aesthetic or consumer choice option in these tables, and they shouldn't be ignored, even if they're not necessarily scientific. Lots of people would prefer to have a larger TVA. They could. Okay, so that's one thing. TVA has twice the efficiency of TVB is a scientific thing. So you can see here, once again, the word twice represents a calculation. I've noticed that 80% is twice 40%. You get credit for doing that. Now, to get the very highest marks in this question, we'd need to use these last two rows together to do a calculation and compare between the two TVs. So what the table has given us is the power output of the TV. In other words, how much light and sound the TV produces, because that's the useful power output from the television. Okay, but what we pay for in terms of electricity is the power that comes in. Okay, so we can actually use the efficiency equation, which is in the formula sheet on the front of the paper, to calculate this. Remembering that I think the efficiency equation in the formula sheet has energy in it instead of power, but you can switch power in as long as you do it for both the top and the bottom of the equation. It will still work. Now, if we're trying to work out the power inputs, so how much it costs to run these things, then we need to rearrange this equation, and what you can do is you can switch the efficiency and the total power input between these two here when you're doing the rearranging. So that's what we get. Total power input is useful power output divided by efficiency times 100%. What we've basically done there is multiplied both sides by total power input and then divided both sides by efficiency. Okay, so that's a little bit of a trickier rearrangement than you might be used to, but that's that's the sort of thing we have to be able to do to get these 5 or 6 marks. And then we take the numbers from the table and we substitute them in. So when we do that for TVA, we have 100 watts from the table power output and we have 80% efficiency. That means our power input is 125 watts. We should always get a larger number for our input than our output, because obviously that means 25 watts of this is being wasted as thermal energy. Okay, that's where that extra 25 watts has gone. And for TVB, we get a power input of 200 watts. So now we have this data, right? We can now compare these two things which weren't in the table, which are very useful because they're basically the running cost of the TV. Higher power input means greater amount of electricity required, means higher running costs. So here we go. From the calculations, we see that TVB will cost more to run as it needs 75 more watts. Again, I've done a subtraction to compare them, right? And the important point about that is it at least partially cancels out the extra cost of TVA. Remember we mentioned up here it costs more, right? And it means that during the running of TVA, there will be less CO2 emitted at power stations. So that's linking back to our Sankey diagram stuff we discussed earlier on. If we increase the efficiency and use less electrical power to run TVA, that will mean less carbon dioxide emitted at power stations. Okay, and then our final bit is our balanced conclusion. And I've gone for TVA, just saying, although it costs more to buy, it will cost less to run, and it offers a better viewing experience because it's 40-inch rather than 36-inch. Obviously, we don't have any information about things like picture quality, but if we don't have any information, we can't say anything about that. Some people might argue that the 6 years, 4 years thing is a big deal, and that TVB we'd be better off with just because of that, even though it might cost a little bit more to run. The fact that it lasts 50% longer, it also means that there's a sort of bigger real gap between the cost of them. But again, as I said, it doesn't really matter what conclusion you come to, as long as it's not like really obviously one is better than the other. Here, there's a balance of points on either side, so you can choose whichever one you like as long as it is justified. Thank you.